We present SANDO, Safe Autonomous Trajectory Planning for Dynamic Unknown Environments. Many existing approaches use soft constraints to handle dynamic obstacles. However, soft constraints do not guarantee safety and can lead to potentially unsafe trajectories. Others use hard constraints, but these are often overly conservative, considering only the worst-case reachable region. To address this, we propose SANDO, which guarantees safety while achieving less conservative performance. SANDO introduces spatiotemporal safe flight corridors, or STSFCs. STSFCs construct polytopes across different time layers and consider the reachable set at each layer, avoiding over-conservatism while maintaining a continuous safety guarantee. Here is the temporal view. By accounting for the temporal aspect of dynamic obstacles, STSFCs produce safe flight corridors that are significantly less conservative. Our main contributions include 1. STSFCs, 2. A heat map-based global planner, 3. A mixed integer quadratic programming formulation designed to work well with STSFCs, and 4. A formal safety analysis of SANDO. Finally, 5. We conducted extensive simulation benchmarking and hardware experiments. First, we show a simulation run in a static environment. The trajectory is color-coded. Green indicates faster speeds and red indicates slower. The orange points represent occupied voxels, while the sky blue points are unknown voxels used by the global planner and safe flight corridor generation. The green polytopes are the safe flight corridors. Next, we fly SANDO in a dynamic environment, interactively assigning random goals by clicking in RViz to set each next goal location. The goal is visualized as a green sphere in RViz. Here, we showcase that SANDO can safely navigate highly dynamic environments at high speed. We will open source our code so you can try SANDO for yourself. We benchmark SANDO in dynamic environments against state-of-the-art planners, FAP, Intent MPC, and Ego Swarm 2. SANDO achieves the fastest travel time while maintaining collision-free flight. Here is a hardware demonstration of heat map generation and the global planner. The dynamic obstacles location is estimated and tracked using point cloud data from a LiDAR sensor, and its future trajectory is predicted. You can see the heat map generated around the dynamic obstacle and along its predicted trajectory. The global path, shown as red lines, avoids the high heat areas. We performed hardware experiments with different types of dynamic obstacles. An autonomous rover follows 3 different trajectories across the experiments: a line, moving back and forth, a circle, and a figure 8. We also had a person walk around randomly in the flight environment. SANDO achieves safe flight in all scenarios. Finally, we flew an agent with 5 dynamic obstacles. SANDO performed a safe round trip across the 20 by 8 meter space. All perception, localization, mapping, planning, and control run entirely on board in real time, with an average total replanning time of less than 25 milliseconds. As you can see, SANDO successfully achieves collision-free flight, avoiding multiple dynamic obstacles. Thank you for watching. Please check out our paper and code on GitHub.